So you've got the basic rule for a logarithm and how to take the derivative. Rule itself is easy. We're just going to apply it to some increasingly complex problems because not only do you have just a logarithm, but you might have the chain rule in a logarithm, and it's just the logarithms are kind of big, but the rule is the same. So here is how it goes. All right, if you start with a logarithm of u, okay, u on the inside could be a simple, very simple thing like x, or it could be very complex like a trig or a square root or something else that you've got buried within there. If we are going to take the derivative of that, so the derivative of the logarithm with a u on the inside, the rule for the derivative is as follows. It's the reciprocal of whatever u is. So it's 1 over u. But then you have to use the chain rule on that. And the chain rule would be then also the derivative of whatever u is. So it's the reciprocal of u times the derivative of u. And that is how you take the derivative of a logarithm. It's pretty basic. We're just going to practice it with functions that are going to start out simple and then move to the more complex as we go. So here's some intro examples. All right, we are going to differentiate. Okay, just remember the reciprocal of u times the derivative of u. Okay, if we have the natural log of x plus 2, and we are to take the derivative of that, so d dx of the derivative, or we're going to find y prime. So this derivative is pretty simple, because it's the reciprocal of u, which is 1 over x plus 2, times the derivative of u, which happens to be 1. So that's about as basic as it gets. All right, here's another one. Suppose you have the natural log of the square root of 3x, and you're taking the derivative of that. Okay, the derivative of that would be the reciprocal, so the square root of 3x, and then the derivative of that. So as you take the derivative of the square root of 3x, how do you really need to think of 3x? 3x quantity to the half. It's not the square root of 3 separate from a plane x. It's the square root is applying to the whole thing. And so our chain rule would be multiplied by half of the quantity 3x to the negative half, which then needs a chain rule on top of that, which gives us 3. And we never want to leave the negative exponents, and so we would clean this up. So our numerator would just be the 3. The denominator would have a 2 from the half. It would have a square root 3x from the first one that we had, the first reciprocal, and it's going to have another square root 3x because of the chain rule, which gives me 3 times 2 times the quantity 3x, which simplifies down to 1 over 2x. So there's a lot, once you get past the initial rule, then you've got the chain rule and the simplification and stuff to get it down to its more simple form. Okay, C. If we have the natural log of 1 over x, and we need to take the derivative of that. So that's going to be the reciprocal of that, which is what? Just x, times the chain rule derivative of 1 over x, which I need to think of as x to the negative first. So the derivative of x to the negative first is negative 1 times x to the negative second, times the chain rule on that, which is 1. So this simplifies to negative x in the numerator and x squared in the denominator, which becomes negative 1 over x as the derivative. Okay, any questions on that so far before we move on to a little bit more complex functions? Okay, all right, so then what do you do for other logs? Because I only gave you the rule for which kind of log? I only gave you the rule for natural logs. And so then you got it, what do you do if you have other logs? Okay, so let's start with that. So what if you have the log of a base and it's not the natural log? And what if you want to take the derivative of that? So the rule for that is that before you do the derivative, you have to use your base change rule, which comes back to what you learned in Ham about logs of different bases. Okay, there's a base change rule that says that the log of any base can be rewritten as a natural log divided by the natural log of a constant. That's called the base change rule. It's taking a log that's not a natural log and converting it into a log that is. And we want to take the derivative of that. So you want to always do the base change rule before you do your calculus. Then you might think, oh, well, does that mean I got to do the quotient rule to this if I'm going to take the derivative? And the answer is no, because b is what kind of number? It's a constant. And if b is a constant, then what's the natural log of b? It's still a constant, isn't it? Okay, the fact that you're putting a natural log around a constant doesn't change it. It's not a rational number, it's irrational, but it's still a constant, which means you can pull it out to the front. And then all you have left is the regular derivative of the natural log of u. So that helps out a lot, the fact that you can pull the constant out. Which means then I just have the regular rule to follow. So overall I've got 1 over the natural log of b, which is pulled to the front, and then the regular rule, which says do the reciprocal, and then the chain rule. So look at the overall result. What's the only difference between the original rule and this rule? The 1 over the natural log of b out front. That's the only difference, okay, ultimately. All right, so we've got that as sort of a corollary to the original rule. Oops. And so we can use that to do some additional examples. Where we're asked to differentiate. And so this will be example D. Okay, if we want to do the log base 10 of 3x plus 1, and we want to find the derivative of that. So basically, to simplify that, we would have 1 over the natural log of 10 instead of the common log of 10. And then times the reciprocal, 1 over 3x plus 1. And then times the chain rule of that, which would be 3. And so you would write that as a numerator of 3. And then you probably want to write natural log of 10 in its own quantity and 3x plus 1 in its own quantity, just so you're separating. You would not want to mislead someone who's reading your work into thinking that the natural log of 10 was like multiplied by 3x or something strange, so you want to make sure you keep those isolated in their own parentheses. Okay, let's try another one. And so if you're taking the log base 5 of the cube root of x, and you want to take the derivative of that. So since it's not a natural log, but it's another log, we would have 1 over the natural log of the base of 5. And then the reciprocal, 1 over the cube root of x. And then the chain rule of the derivative of the cube root of x. So we got to think of that as x to the 1/3. So that would be 1/3 x to the negative 2/3. And we wouldn't want to leave it like that, but we'd want to clean that up. So that's going to give me a numerator that's just 1 over. The denominator would have the natural log of 5 and the cube root of x. I'd also have a 3 from the 1/3. And then I'd also have the cube root of x squared. That's x to the negative 2/3. So I've got a cube root of x, and I have a cube root of x squared, which could combine together to be the cube root of x cubed. So we're really looking at 1 over 3, the natural log of 5, and then just plain old x on the end. Okay, any other questions on that one? All right, so last section of the notes. Okay, logs also provide an alternative to the power rule. When neither of the base or exponent are constant. Oops. Okay, so let me explain what I mean by that. If you have x to the b, we're going to use the power rule. Because the b is the constant and it's in the power position. If we have b to the x, then you're going to use the exponent rule, which you just learned. And that's when the base is the constant. Exponential, sorry, not just the exponent would be the exact same thing. Exponential. Okay, so then the other option is, well, what do you do if it's x to the x? You can't do the power rule because the power rule only works when you have a number that you can subtract 1. You can't use the exponent rule because the exponent rule requires you to have a constant base. And so we're going to use logs in that situation. And we're going to do logs first, which is kind of why I snuck that little thing in with Jake earlier today about the natural log of 9. And I showed you that. I snuck that in. Okay, so let me show you what I mean. Let's do an example where we want to apply a log first. All right, so this is example, what are we up to? A, B, C, D, E, F. Okay. So suppose we have secant x to the tangent x. And we want to find the derivative of that. Now, you can't just move tangent to the front and subtract 1. That's always one of the multiple choice options to catch the people who think, oh, I'll just move tangent to the front and I'll minus 1 and I'll be done. Okay, that's not how that works, but it's always there as an option. What you want to do is apply a natural log first. So around the y, you would apply a natural log, and around the opposite side, you would apply a natural log. Now that's not very exciting on the y side, but on the secant side, it allows you to pull the power to the front, because that's one of the rules for logarithms. And so that's going to give you the natural log of y being equal to tangent of x multiplied by the natural log of the secant of x, which then allows us to use the product rule here. On the left side, we're just going to use the regular logarithm rule like we've learned, which is the reciprocal times the derivative. And so the reciprocal would be 1 over y, and the derivative would be dy dx. On the other side, I'm going to use the product rule. Okay, the product rule is going to have me identify an a and a b, so I'll have part A, I'll have part b. My product rule would say start with part b, which is the natural log of the secant of x, and multiply that by the derivative of tangent, which is secant squared, plus, now do a part, which is tangent of x, and multiply that by the b part, which is a logarithm. And so that would be the reciprocal times the derivative. So the reciprocal would be 1 over secant x times secant x tangent x. What do you notice happens in that last set of derivatives I just did? Yeah, the secant x can reduce away. So that's leaving me with 1 over y dy dx being equal to, now you can't combine those secants. You can't say the natural log of the cube of secant. One is the natural log of secant x as its own quantity. The other is secant squared x as its own quantity. Plus, and then when I reduce the two secants, I'm left with tan squared. And you've seen this before. We just need to get dy dx alone. So what do we do to get dy dx alone? Multiply by y. So dy dx by itself would be y times the other side. And what was y to begin with? Okay, y to begin with was secant x to the tangent x. So your final answer would be secant x to the tan x times the whole quantity, the natural log of secant x times secant squared plus tan squared. So just put a bit, you don't have to distribute, you don't have to like clean it up or anything, just leave it, you know, undistributed like that as your final answer.